Okay, so this is the formulation of Kiefer's theorem. And these are the ideas, right? So idea is just to find sufficiently large family of contractions for which you have large deviations. And then to use this idea, the property P, to prove that property P, we said that the rate function does not depend on the sequence. Well, it turns out that this can be separated into two tasks. And the first theorem is a name. The first part is a name called Dousona-Gартнера, the same Gardner, I believe. And I add here Pухальский, because in the initial formulation of Dousona-Gартner, the formulation is not easy. It involved the concept of projective limit. Pухальski's contribution is that first, we notice that if you have exponential tightness, which means that you have compactness, then you can really simplify the formulation. And also, it shows that how to use this to prove large deviations. So here is the result. Well, now it is not important that you have probability measures over compact space X. So I will formulate result in the general setting. All right. X, the compact metric space. Right. Psi be a sequence of X graded random variables. And right, phi gamma, I'm sorry, forget this, just the definition. Let us consider set with partial order. Which I can denote by this symbol. So we consider set G with a partial order. Shall I remind you what it means? The first condition is that if you have two elements, if one second. So you have gamma 1 and gamma 2 in G. I'm sorry, no. Gamma 1, gamma 2. Partial order is that contain diagonal, already gamma. Gamma is smaller than gamma. The second condition is that for any gamma 1, gamma 2 in G, if gamma 1 is smaller than gamma 2 and gamma 2 is smaller than gamma 1, then gamma 1 is equal to gamma 2. So it is reflexive, it is antisymmetric, and it is transitive. For any gamma 1, gamma 2, gamma 3, if gamma 1 is smaller than gamma 2 and gamma 2 is smaller than gamma 3, then gamma 1 is smaller than gamma 3. And in addition to this, right, so this is the usual definition of partial order. Think of finite subsets of any set. Right? You take any set, for instance, a set of continuous functions, and you take all finite subsets. Then obviously all these properties are true. In addition to that, I will add the last property, which says that for any gamma 1, gamma 2 in G, there is gamma in G such that gamma 1 is smaller than gamma and gamma 2 is smaller than gamma. Again, if you consider the case of finite subset, it's so true. Just take the unit. Now I have two objects, a compact metric space and a set G with partial order, which means that these four properties are satisfied. Now let's come back to the theorem. So we have a sequence of x-independent variables and continuous functions from x to x gamma, where x gamma is just a metric space, is a Polish space. In fact, we can assume that it is compact because it is the image of x is by continuous. It is the image of x by pi gamma is contained in x gamma. But the x is necessarily compact, so we can always assume that the x gamma is compact. And gamma belongs to gamma, a set with partial order. Okay, so we have a sequence and a family of continuous maps. Continuous. Gamma continues, such that the following properties hold. The first condition is monotonicity. And it says that for any x, x coming graphic, the family right here, A gamma x, which is by definition phi gamma minus 1 for phi gamma x, is decreasing. What it means that if gamma 1 is smaller than gamma 2, then K gamma 1 x larger than K gamma 2 x. In addition, the intersection of K gamma x when gamma is in G is a singleton x. Okay, one second. We have a random sequence in X. We have a lot of maps from X to X gamma. This gamma belongs to set G, so these spaces and functions are indexed by a gamma, which belongs to a set with partial order. And then we assume the following two hypotheses. The first one is monotonicity. It says that if you fix X, you consider the image of this X and the inverse image of this singleton. There can be many points. This is a singleton, but this one, it has many points. It is a compact set, right? Because this is a singleton and compact. Phi gamma minus 1 is the inverse image of a closed set, so this is closed, and it is a subset of a compact set, therefore it is compact. So assume that this family is decreasing, which means the following: the larger this gamma, the smaller the set. And in addition, if I take the intersection with respect to all gamma, then there is only x left. Right, so you take k gamma x. You increase your gamma, this set gets smaller and smaller. In principle, in the intersection, there can be many points. The hypothesis is that, in fact, there is only one point in the intersection. So this family is sufficiently rich. If you have a point, you can localize it by considering all the sets, k gamma x. Now, second hypothesis. Right, L, D, P with index gamma. It says that for any gamma, n, I gamma psi n satisfies LVP the right function, which I denote by I gamma. So I gamma will be lower semi-continuous function from x gamma to R plus bar. I'm sorry, I don't see Polish space, but let me write compact space. Because it is not a restriction of generality, as I explained. The phi gamma of x is included here, and it is compact. Two hypotheses: monotonicity and the fact that it is sufficiently rich so that to localize x, you need to know all k gamma x. It suffices to know all k gamma x. And for any gamma, this sequence satisfies the large deviation principle with some right function I gamma. So these are the two hypotheses in Dousona-Gартnera-Pухальского theorem. Then psi n satisfies the LDP with the right function, which can be written explicitly, Ix equal to the supremum, and gamma is in G of I gamma, phi gamma of x. This theorem is a formalization of this idea that if you have a sequence and sufficiently a large family of contractions satisfying the LDP, then the initial sequence should satisfy the LDP. Okay, let's prove this result. Now the proof is almost the same length as the formulation. Now, it suffices to check that psi n satisfies property P. Right?
Is it important that in this series that are the space x gamma depends on gamma? So it's really the case in application.
Yeah, because I mean, we have those applications, right? From X to RD.
Now you edit it. So it's dimension after dimension.
Yeah, I mean, not only dimension, but this in space described by, yeah, you can say dimension, yeah, same dimension. Okay, so we need to check property P, which means that if you have a sequence, so which means that this if a sequence, let nk going to plus infinity is such that you have that usual relation, right? The limit is k goes to infinity, 1 over nk, logarithm probability psi nk is gamma is equal to dotted out minus I of gamma. Sorry, let me write here J. One second, what's what I'm saying? Just 1 second. What I'm saying here. Yeah, sorry. So let B such that you have this. So let us choose a sequence for which this is true. What we need to prove that this I does not depend on k. I mean, in fact, we do two things. One, first, we choose such a sequence. Then, assuming that this relation holds, we shall prove that I does not depend on this sequence nk. I can describe I explicitly using those functions I gamma.
So he didn't assume the explicit form of I written above. This is just any I. Right?
Yeah, just I gamma. I, what do you mean by I?
Yeah.
This I.
That I in the formulation is still like that I.
Yeah.
I.
So in the formulation of the theorem, you have written the explicit form of I,
Yeah.
but for the moment you do not
For
assume.
the one I don't assume. Okay, let me write in J. Let me write in J to make sure that there is no confusion with that I. For that, you have this relation where you need to prove that J does not depend on k. This is what we need to do, right? Now, by the contraction principle, I can apply contraction to this formula to conclude that the limit as k goes to infinity, 1 over nk, logarithm probability. Now I'm writing phi gamma of psi nk belongs to gamma. This is equal to what? Is equal to minus j of phi. Okay, so it's a function to have this gamma here. Let me write the gamma prime. Phi gamma minus 1 of gamma prime. Gamma prime is a subset in x gamma. Gamma prime belongs to B of x gamma. But on the other hand, I know that this reduced sequence, this contracted sequence, satisfies the LDP with the wave function I gamma. On the other hand, the limit without any subsequence as n goes to infinity, 1 over n logarithm probability that phi gamma of psi n belongs to this gamma prime is equal with a dot to minus I gamma of gamma prime. And so on the one hand, for subsequence, we have this. On the other hand, for the root sequence, we have this. Now, this is true in particular if you replace n by mk, and by the uniqueness of rate function, you should have it forward to the end. By the uniqueness of the rate function, for any gamma, and for any gamma prime, d of x gamma, we should have I gamma, we should have j of phi gamma minus 1 of gamma prime is equal to I gamma of gamma prime. Right, so we get with the two relation principle for the same sequence, these rate functions will be the same. Or the rate functions should coincide on all sets. So let us take here gamma prime just phi gamma of x. Right? I have the right to take gamma prime equal to phi gamma x, which is a closed subset. Then what I get is the following: j of what I denoted by k gamma x. Right? So if I replace gamma prime, the k gamma prime equals so that
f to the power minus 1.
just 1 second, phi gamma minus 1 of gamma prime is equal to k gamma of x. Saying Armen?
No, it's a d.
Right, so if I take phi gamma prime phi gamma x, then phi gamma minus 1 of gamma prime will be phi gamma minus 1 of phi gamma x, and this is exactly my set k gamma. Right, so you have j on k gamma x. J is this function, right? J on k gamma x is equal to I gamma of phi gamma x. Okay, let's now see what we got. We had a rate function j, and we want to prove that this rate function is the same for all sequences nk. Right, this is our goal. Property P says that you need to check that for any sequence for which large deviation principle holds along the subsequence, the corresponding rate function is universal. It does not depend on nk. Now we apply contraction to this in this relation. On the other hand, by hypothesis, not only the subsequence, but the whole sequence satisfies the large deviation principle with the rate function I gamma. Comparing this with this relation in which n is equal to nk, you have the same left-hand side, so the right-hand side is the same. So we get for any gamma prime this relation, and for any gamma. So in particular, if I take gamma prime equal to phi gamma x, I will get j, which is unknown, but for which I want to prove universality, is equal to this one, which is independent of anything. For the moment, I can't say what is the value of j of x, but I can say what is the value of j of k gamma x for any gamma. Then I will use this condition, which says that this x is identified by all this set k gamma x. Now to conclude, I need the following lemma. Now I make the following. It says that if j is lower semi-continuous, And K gamma is a decreasing family of compact subsets of X. Then, if I want to calculate G, J on the intersection, I need to take the supremum. Yeah, I need to take the supremum. Let me erase this part before discussing why this result is true. Let me just keep Gardner-Ellis. It's okay. I have up to this point. It's more or less clear what we did. Let's discuss this later. So we have a lowest and continuous function and a decreasing family of compact subsets. It is independent from anything. Then the claim is that the infimum over the intersection is exactly the supremum of J of K gamma. Let's suppose that this K gamma is a sequence, decreasing sequence of subsets, right? So you have K1, K2, and so on. K1, K2, and so on. This is the intersection of Kn. Let's consider the counter of this. Let me not K, the intersection of Kn. Then obviously the infimum over K is greater than infimum over Kn for any n. And the larger the set, the smaller the infimum. This is a increasing or non-decreasing sequence. Therefore, it has a limit, and the limit will be exactly the supremum. Jk is greater than the limit of Jkn, and n goes to infinity, and because this is a non-decreasing sequence bounded above, the limit will be the supremum of Jkn. The lemma says that, in fact, it is equal in G of what is written there, J K gamma X, and finally J K gamma X is this one. It is I gamma on phi gamma of X. So we started from J of X and ended up here. As you can see here, there is nothing depending on NK. Right, so this proves Dousona-Gартнера-Pухальский theorem.
Property P is a being.
Yeah, property P. Okay, property P is the following. If NK going to plus infinity and a rate function J the same as before are such that well, let me say L D P holds for psi NK with rate function J, then J is equal to some universal function I. Now, I didn't say who is that universal function. Now I can say that that universal function is exactly this one, which was mentioned in the theorem. Of course, you need to prove that this is a lower semi-continuous function, but it's really not a big property, so we will not discuss it. We didn't say we didn't prove that this is lower semi-continuous, but it is really not big. Basically, you need to consider the set I is smaller than C, and then the supreme is true if the intersection is there, and so on. "25 minutes left. I will skip. I won't discuss at all Donsker's theory. It will be about
No chance, no chance.
yeah. So let's see how we can apply this theorem to a sequence mentioned here, right? To prove ether theory.
Which has some applications, whatever you want.
Applications.
Yes.
Okay, so application is just Donsker's theory. We can discuss that instead of the proving ether theorem, we can discuss Donsker's theory.
At least discuss the maybe.
Yeah.
Maybe.
Okay, so let me just 1 second. Okay, so let's do the following. Let's just consider the staging. Okay, so in the third section, Donsker's theory. Well, it is indeed a theory because it is not about just one theorem. It is just a general idea, a general approach for obtaining large deviation principle for Markov forces or Markov chains. Okay, now we consider again X, which is a compact metric space. And we consider a Markov process. Discrete time Markov process. Discrete time Markov process in X. So I'm using the convention that I have one trajectory and a family of probability values. Then I can define two objects. The transition function what is the transition function? It depends on the integer k, which is the time on the initial point x and the set gamma. This is the probability that the process starting from x belongs to gamma time k. And then you can define Markov operators. So, as usual, there are two families, pk acting in the space of continuous functions and pk star acting in the space of probability measures. So pkf at the point x is integral over x f of y pk x dy, and pk star mu on a set gamma is integral over x pk x gamma mu of dx. Just usual definition of Markov force of transition function and Markov operators. We introduce a family of random measures. It is called empirical measures or occupation measures. Nu n is 1 over n, the sum k from 1 to n, direct mass at the point xk. So xk is a random process in x. Delta xk is a random measure in x. So this is an element of x calligraphic. It is a random element of x calligraphic. So exactly what we had before. So nu n is a sequence of random variables in P of x. So the goal is to study large deviation principles. Goal LDP for nu n under the law px. So we have a lot of probability measures. We want to understand if this sequence of empirical measures satisfies the large deviation principle. Or you can prescribe any initial measure instead of deterministic initial condition.
Yes, so this is average number of random points in a set. We have a set.
Yeah, you can say so. Yeah. Or sometimes it's called occupation measure, and it's exactly you take a set and you look what proportion of time the process spent on that set. Okay, now the theorem. Okay, I think it will take more space than this. Rising function.
Yes, so what numbers apply to it?
To this one?
Yes, yes.
Yeah, but when I put the condition, then yes, yeah, it's a bad form.
So this is a specification of strong law which now. So
Yeah.
but there were no conditions so far.
Yeah, so far there are no conditions. There are two conditions which are going to impose, and
Out.
don't immediately that these are stronger than usually what you, well, more or less what you usually impose to have mixing, exponential mixing and everything else. In theorem, and this is Donsker's-Varadan. So suppose that the Markov process satisfies the following two hypotheses. Xk dx satisfies the following hypothesis. The first one is strong irreducibility. So, just 1 second. Just to be sure that formulate in right way. Any uniformity. So for any R, there is an integer m such that for any x and for any ball b of radius r, this is the same r, we have the probability of transition from x to b at time n infinite, sorry, for any epsilon, for any for any m, there is for any r there is m and there is p. Such that PMXP is greater than P.
There exists M and there exists here.
Yeah.
There exists M.
So you fix what? You fix R. Then you can construct the time N, so this is the time, and P, this is the probability. So that if you fix any initial condition X and any ball of radius R, then in time M, the probability of being here is at least T.
It's only on the radius of the ball.
It depends only on the radius of the ball. Yes. Well, of course, these conditions are not optimal. You can weaken them, but it's not the goal now. The second is uniform Strong-Feller. Says that for any x in X, the limit of P, let's take 1 y dot minus P1 x dot. I compare these two measures. So these are the transition functions from x and y, and I calculate the distance in the total variation metric. And I calculate the limit when y goes to x. And this should be 0. Yeah, so this is a bit stronger than Strong-Feller. Strong-Feller said that you have continued, if you fix the gamma. Yeah, but I mean, this is, yeah, it's going to be weaker. I mean, this is not, well, this is perfectly satisfied, for instance, for stochastic differential equation for
Final
dimension. Yeah, sure. No, of course, it does not apply to these. Then Strong-Feller says, Strong-Feller. What is Strong-Feller? For any gamma, dx, the function x, p1x gamma is continuous. Or, in other words, the limit of p1 y gamma when y goes to x is equal to p1 of x gamma. For any fixed gamma, this is the Strong-Feller property. Transition function, if you put there, let's say gamma is a continuous function of the initial point. Now, I say that it should be true in the total variation metric. Well, if you consider, for instance, stochastic differential equation of a manifold, or if you consider differential equation with random coefficients with some non-degenerate randomness, then this is satisfied. It's not difficult to prove that you will have a density and so on. So you have two hypotheses: strong irreducibility and uniform Strong-Feller. Then for any x, the sequence nu n, so that nu n is the sequence of empirical measures, satisfy the LDP. Linear function which you can write explicitly. I of mu is equal, if you take the supremum over all strictly positive functions, integral over x, logarithm p divided p1 by 2v and dv.
But it shouldn't be x
Yeah. Yeah, sure, things.
Is here X calligraphic element.
X calligraphic is right here. X is just compact metric space.
Yes.
And X calligraphic is space of measures on X.
Then wait, then the storm that you say B, then not my name.
Yeah.
I know it's now and a little bit lower.
Yeah, they also, yeah. Yeah, so let's we have something like 5 minutes left, maybe more. Let's discuss
Who is P1? Who is P1?
P1 is the time on transition function. Transition function.
Wait, then who is the user? Break is on this, right? Break is on this.
No, just P1B. I mean,
No, I
no, PKF, right? So P1F, and that is P1B.
So super all positive functions.
I think you should know all positive functions.
Functions, okay.
When it is positive, it will be bounded away from zero.
Okay, fine. We go.
So let me just tell you just one thing about some ideas, right? Some idea. Well, according to Hipper's theorem, we need to study this object. So let us write what is there. So Q of V is what? Is the limit as n goes to infinity. And I need to take V mu n. Let's calculate here mu n before I can give you the formula. V mu n multiplied by n. So I have n and I have V 1 over n, the sum k from 1 to n delta xk. Right, so this is the integral. Now this n simplified with this one, and I get the sum k from 1 to n, we integrated against delta xk. But integrating against the Vera class is not difficult. We get the sum k from 1 to n v of xk. What we get is the following: 1 over n logarithm mean value exponential of the sum v of xk. By the way, I didn't mention that so it is written here something which is independent of x. So in particular, the rate function is the same for all initial conditions. So in principle, here this q may depend on x. Now, let me continue here. We have 1 over n logarithm of something. Well, it turns out that this expression Ex exponential the sum k from 1 to n v of xk is equal to an operator. Again, I can formally write it as E and V applied to the function identity equal to 1 at the point x. And what is this P and V? P and V applied to function f, the point x, is this expression multiplied by fx. Ex exponential v of x1 plus v of xn f of xn. Right, so once again, I need to calculate this logarithm of this expression divided by n and n goes to infinity. Now let's consider the expectation. The claim is that this expectation can be written as an operator which I denote by P and V. It depends on n, it depends on V. So V is here, n is here. Applied to a function identical equal to 1 and calculated to the point x. So how I define this operator? P and V on the function f, the point x, is exactly this expression multiplied by f of xn and averaged with respect to px. Right? So for the moment I didn't say anything. Now claim, and it follows from the Markov property the claim is that P and V is a semigroup. And its generator, with the generator, well, of course, the generator of a discrete time semigroup is just the semigroup at time 1, right? P1 V f of x is what? Is this expression when n is equal to 1? But I can write it using the transition function Pn x dy exponential v of y f of y. So we see clearly the connection between the pressure and the behavior of the semigroup, which is called Feyman-Kats semigroup. Right, so QXV is Feyman-Kats semigroup applied to the function identical equal to 1, and after this operation, logarithm 1 right do it. Which means that if I know the behavior of the Feyman-Kats semigroup as n goes to infinity, then I will know something about the pressure and properties. This is why we need, well, in the case of stochastic differential equation, this Feyman-Kats solution of the Feyman-Kats semigroup is just a solution of the parabolic equation with the potential. So this is somehow clarifies why we need those conditions, because these are more like the conditions which show the regular behavior of this Feyman-Kats semigroup this time of semigroup. I think it's a good time to stop, and I thank you for your attention.
What is your favorite reference? What's your favorite
About what?
knowledge derivation as a whole?
Well, it depends what you want to study in our divisions. I mean, there are still really a lot of books. It's really difficult to say. I mean, because it only covers really a lot of subjects, but sometimes it can be complicated and very formal. Then one there is also it's more trained, but we
Less complicated and less possible.
for what? For what? For Markov process. Yeah, it's difficult to say for Markov processes. I mean, many people consider like the Markov processes And there are really a lot of general results. I mean, these conditions are very, very strong compared to what we have in the literature.
Yes.
Yeah, so for instance, deposit to me is that type of result. Yeah, no, normally it's the case when you don't have strong failure.
Yes.
Before our actions became necessary.
Yes, and compactness, this restriction.
Yeah, it really simplifies, but even with the compactness, you really have a lot of things to do.
Yes, of course.
Without compactness, it is getting rather complicated technically, but it can be treated. And maybe just another thing is that this is not the final result of Donsker's theorem. Donsker's theorem deals with this is called level 2 large deviations. And instead of considering functions, we consider the measures. But you can consider the full trajectories from time 0 to infinity or time k to infinity. And when you do that, you get another formula for the wave function. It is called Donsker-Varadan entropy, and it becomes affine with respect to the measure. It should be, which is really the property of entropy. Fine properties. So this is the full result is about level 3 large deviations.
This is true that under these conditions you have mixing, right? Or,
Yeah, definitely. Yeah, exponential mixing.
yeah. You also should represent the mixture theory.
You also have something.
It does imply large relations for observables.
Yes, it does, because if you want to study large deviations for, I mean, what do you mean large deviations by observables? I suppose that you want to have observable, and you need to consider this.
So you apply your empirical method with something.
Yeah, and this is precisely f applied to mu n. So you have large deviations for this one, therefore you have large deviations for this one for any continuous function.
Yeah, I said no. I'm speaking from the other hand. If you have central limit theorems, then does it imply but
Central limit theorem for what?
okay, you have central limit theorems for this sum, which you have written down.
This one.
Yes.
Does it imply large deviations? This is, oh no,
No.
no, I mean, it's much finer. I mean, large deviations, it is not true that large deviations apply central limit theorem, but with some conditions on this function, for instance, if it is analytic in the neighborhood of 0, then large deviations do imply central limit theorem. But not by itself, no, central limit theorem is, no, it's not treated, it's different to that. I think that's okay.
Big joke.